Hello, and welcome to today's session on the perfect IIoT platform. Before we jump in, I wanted to take the opportunity to thank the Industrial Internet of Things USA team for putting together the conference and for giving us the opportunity to share our thoughts on this very important topic. I thought we'd start by introducing the speakers. So I will go first. The name is Markus Larsson, and I am the head of PARC's predictive maintenance practice. And I've been a member of the executive management team of PARC for 4 years now. And prior to that, I spent about a decade working on various forms of corporate and startup innovation initiatives, largely centered on forming various forms of commercialization or innovation partnerships worldwide in both industrial and consumer sectors. And I have a master's degree in industrial engineering and management from Chalmers University of Technology in Gothenburg, Sweden. So with me today, I have Dr. Kai Goebel. So Kai, would you like to introduce yourself?
Yes, Markus, thank you. I'm a principal scientist at PARC. I have worked almost a quarter of a century in predictive maintenance fields. They weren't always called predictive maintenance, of course, not just at PARC, but also at NASA and at GE. And I've worked really on a number of different application areas, which include manufacturing, energy, transportation, medical systems, and of course, aerospace. I hold 18 patents in the area, have published a good number of papers, including one book on prognostics, and I have a PhD in mechanical engineering from UC Berkeley.
Excellent. Thank you, Kai. And for those who may not be familiar with PARC, we are a part of Xerox Corporation, and we have a long history of developing and delivering breakthrough technologies that make life better for humans and increase productivity for businesses all over the world. And in fact, this year, 2020, is our 50th anniversary. We turned 50 on July 1st of this year. And we're, of course, looking forward to another 50 years of delivering breakthrough innovation to all over the world. And just related to the topic at hand, we've been very active in various forms of prognostics and sort of more broadly speaking, IIoT technology and product development for a good couple of decades now, starting with things like industrial printers, obviously in predictive maintenance for those, or prognostics, health prognostics for those, and evolving that into capabilities that now serve a number of different industries: transportation, industrial, power, and so on. So kind of from that context, we're quite excited to share with you today how we think of the evolution of IIoT platforms into perfection, such as the topic is. So just in terms of what we're going to talk about, we want to start with sharing a little bit of how these industrial IoT capabilities have evolved over time, and including some of what we think those shortcomings are today, with a particular focus on predictive analytics and predictive maintenance types of applications, before we share what we think the future holds for IIoT platforms more broadly. So maybe Kai, we can start with your thoughts on how industrial IoT has evolved over the sort of longer arc.
Yeah, thanks, Markus. So IoT really rides on the back of this broader digitization effort that we see for industrial assets and the supply chain. And in particular, we see these new initiatives. They have names such as Smart Factory or Industry 4.0. And they have provided visibility to the benefits of digitalization in an industrial setting. However, the penetration of these kind of initiatives is not the same in all industries. Some have been more aggressive in adopting the principles, such as industries such as aerospace, oil and gas, or fleet management. But the application domains are really manifold, right? So some digitization efforts focus really only on improving logistic processes, and others have shown provide benefits for operations through predictive maintenance.
I think that's exactly right. And one thing we often see or hear, particularly as we're here in Silicon Valley, where everything moves at lightning speed, that a lot of outside observers, or people who are maybe not inside of heavy industries and inside of heavy industries generally, are a little surprised by the sort of pace of evolution here. And it's sort of obviously for solutions like this, you're not only dealing with bits, as we're used to mostly in the Valley, right? But you're dealing with atoms, and you're dealing with an existing stock of production equipment that needs to be retrofitted or instrumented in certain ways to make it useful or make it IoT enabled, such as it is. So obviously that is a time-consuming and quite laborious process to get that done. And it's not quite like distributing software over the internet, where everything can happen on a moment's notice. So there's been a lot of evolution happening there. But one area that I think has caught a lot of people's attention recently is the advances in data science. So Kai, do you want to share your thoughts on that?
Sure. Yeah, I mean, news really are abuzz with how machine learning in general and deep learning in particular has made revolutionary progress. And this has been demonstrated in the ability to being able to properly recognize and classify images. We all know the Google cats, which may not be quite as helpful for us in an industrial kind of setting, but also to beat humans in games of various complexities, such as AlphaGo or StarCraft, or perhaps more relevant, drive vehicles autonomously in some, although some only reasonably controlled conditions.
Yeah, and I think it's now clear for most observers, certainly out here in the Valley, that while deep learning has some enables some amazingly powerful capabilities, it also has as a technology real limitations. So if you take examples that are widely publicized, like autonomous driving, right? Even after billions and billions of dollars has been invested into developing solutions that would enable full autonomous driving, it's still a fairly remote or faraway possibility to actually make that a reality. And so while deep learning can be a very, very powerful, or can be very powerful to achieve certain ends, when input data quality varies and the objective of the analysis is a little bit of a moving target, which is true in most industrial IoT situations, it's very likely that we're going to need different approaches to complement deep learning or more pure data science-based approaches for delivering the types of capabilities that we think IIoT really needs. And then, one aspect of these industrial IoT capabilities, though, is that these algorithms need data. So sensors have also evolved over time. So Kai, you want to talk a little bit about your views on that?
Yeah, we hear a lot about ubiquitous sensing for generic IoT environments like our homes and elsewhere. So I'm, for example, very grateful for the ability to tap into all the sensors on air quality that are right now being deployed and that help me to understand whether I can go out today or not. But these sensors oftentimes really don't have very high accuracy. For industrial applications and environments, we often need sensors that do have high accuracy. Luckily, sensor capability has also been steadily improving, and we see new sensing modalities that allow us to pick up new phenomena. For example, there are various kinds of nanosensors that can sense the presence of gases. And these improved and sometimes new modalities will help us to add capabilities that can result in additional benefits.
So while on that topic, then, what are you seeing, Kai, as some of the shortcomings of these, industrial IoT or sensing or AI capabilities that exist out there today?
Yeah, you touched on that briefly earlier, Markus. That has to do in part with the technology, but also with the requirements. I see a couple of issues. One thing that we keep hearing from plant operators over and over is that they really want accurate prognostics. So with that, they mean the ability to get information on how much remaining life there is on their various equipment assets. Now, many approaches do promise prognostics, but they don't actually deliver on it, right? So they may give you information about a changing signature, which is an anomaly detection function in my definition, which is important. And it buys you a real-time view of the state of your equipment, and there's certainly value in that. But the ability really to provide an accurate estimate of remaining life remains largely elusive. The other issue is that providing a long enough prediction horizon is difficult. Depending on operational practice, the requirements, how much lead time is needed to leverage remaining life estimate varies a lot. So in some cases, 1 week horizon is sufficient to schedule maintenance. But in other contexts, it may be required to get a 6 months heads up. And as you may imagine, that is considerably harder because the prognostics has to reason over much more subtle changes, and to pick those up and to incorporate that in a high accuracy prognostic is very difficult. It stretches algorithmic capabilities, but it also may require additional instrumentation. Now, and now we're cycling back to that. Most approaches try to pick what I perceive as a low-hanging fruit. Take data from existing sensors, throw a machine learning algorithm at it, and try to get some answers. But machine learning algorithms need a lot of data to really learn, and not just any kind of data. You need the right kind of data, right? So you need to have examples of when faults did happen to recognize them. And for prognostics, it's even harder because you need to have the run to failure kind of trajectories, and you need to have them in sufficient numbers to really train your algorithms. And that's hard. So what we have is tons of data, but not the right kind of data, and that limits our ability to really just turn the on button on the deep learning and press go to produce some useful prognostics.
Yeah, and I can just re-emphasize that even further, right? I mean, I from PARC standpoint, when we have worked with clients over the years on producing prognostic solutions or prognostics technologies in various ways, the lack of high quality or data with high enough quality and quantity to be really truly useful from a prognostic standpoint for production equipment, right? It's almost never there. And it's we hear that from customers over and over again that, it would be great if we had the data, but we don't. And collecting the data is $1 million multi-year type proposition. And even when you have it, you're not quite sure whether it's going to be useful enough to actually produce the prognostics that you need. So another thing that we see quite often, just from a vendor solution standpoint, is that there's often this ambition to market these IIoT platforms that sort of, as that in and of themselves enable broad digitization of entire factories or entire supply chains, even in some cases, as opposed to building solutions, delivering solutions to actual and specific problems. And if you're a CIO or a COO, you're often very attractive about the potential of what industrial IoT can enable. But each of these, making a platform investment, which I kind of think of as a boiling the ocean type of investment a lot of times, it's often very expensive. You know, it requires instrumentation of a broad range of equipment. It requires connectivity into IT and OT systems on all sorts of different plans, and those systems may be different, etc. So it's a huge integration challenge. And in and of itself, the platform doesn't really deliver a lot of return on investment. So what's needed, we think, is a much stronger focus on solving specific problems, whether that's operational in terms of reducing downtime or improving production yield or lowering operational costs or what have you, as opposed to digitization for its own sake. And so we think that the perfect IIoT platform then really allows for that to happen and enables a near-term problem-solving focus. It delivers ROI very quickly while enabling, you know, the capabilities to evolve and solving one problem after another in the general kind of pursuit of digitizing an entire factory or plant or supply chain or what have you.
Yeah, when you talk about evolving, I think we also want to talk a little bit about, you know, what does the future bring for this application area. And one thing that you already touched upon is that it will take some time, so some of the benefits will not be immediate. But we also want to keep in mind, you know, what's the end goal. So we do see an evolution already, right? So early on, you know, what we saw was the realization that the easy problems can be solved first, and that makes sense. And that was fundamentally to just visualize some of the real-time data and make them available to operators so that they could take a look at what's happening and provide insights into how a fleet or a plant is behaving, and to maybe, you know, deal with those inefficiencies that became visible. Even though I should also say that not every industry really has embraced that quite yet. So there's still a few that have to catch up. Then came the first wave of simple algorithms that allowed alerting on operational issues or equipment fault. Next now are more advanced sensing modalities and algorithms that allow us to predict the future of equipment faults. And in a further step out, we expect that information to be integrated with maintenance planning, with scheduling. After that, integration with inventory management and other elements of the logistics chain. You know, all that should really open up more benefits. And the tall pole really far out is the fully autonomous operation that has self-aware and self-adaptive capabilities. It may sound utopian, but considerable progress is already being made for some application domains. And we expect that we will be able to leverage not only the lessons learned, but also some of the methods that have been developed for those other industrial domains. Now, to address some of the near-term shortcomings of data science solutions is, in our view, really to add in physics-based models. So the perfect IoT platform needs to be able to incorporate not only, you know, those data science-based prediction methods, but physics-based methods, as well as other forms of AI as well.
No, I think that's exactly right. And the one thing I would add too, that's I think is really important from the, you know, the perfect solution or the perfect platform standpoint, is that it needs to, or we as practitioners and ultimately as vendors, right, need to recognize that each of these tools or each of these solutions will, you know, not only it's not only a technology type of approach. It also impacts people who work with them, and it needs to coexist or integrate with processes and workflows that are already there. So it's very important to be able to take into account the wide variety of requirements that that will bring, and also to make sure that whatever you produce as an output is intuitive and natural for both, maintenance engineers or people, in the plant, on the ground, who work day to day with your solution, and to, more higher level or higher ups in organizations, plant managers, operations VPs, and so on. That both of those stakeholder groups get the information delivered to them in an intuitive way and in a way that fits with their workflows. So with that, we're basically run out of time here. So Kai, do you have any closing thoughts for the audience?
Yeah, I think if we were to summarize what we talked about, I think that predictive maintenance really is a cornerstone of IIoT. And we expect really that plant operators will embrace its principles as we move forward, just because the benefits are so obvious. On the technology side of things, we have to realize that there is no free lunch. Right? In particular for prognostics, what we need is a disciplined approach to unlock the benefits by predicting equipment failure. We have to model the different fault modes. We have to understand, how do the degradation progress, and when does it hit a failure threshold. We also have to realize that we need to be open and able to the choice of method used for solving this challenge.
Thank you, Kai. And I'd only reiterate as a closing statement that, this is an incredibly important and interesting space for us. That is really, really key for everybody to stay focused on solving problems. And from our standpoint, the data science approaches doesn't really enable the kind of prognostics that we think are needed in the most cases. And we're excited. We're excited to share, both to be active in this space and to, in the future, share more about what we're working on. So with that, thank you all for attending this talk today, and we look forward to the Q&A session that comes after this. Thank you.
Thanks.